Welcome to Introduction to Project Management, Project Life Cycles. This is Lecture B. The objectives for project life cycles are to identify process groups and knowledge areas in project management, differentiate linear, iterative, adaptive, and agile project life cycles, relate life cycle phases to reviews, milestones, and deliverables. Compare various organizational structures as contexts for managing projects. This lecture will focus on the second objective. All of the life cycle models will be examined using a set of project characteristics that will help you discriminate the differences between the four models. The 6 types of characteristics are shown in the left column of this table, detailing the linear model, and we will continue to use these 6 characteristics when we discuss the other models. Reviewing these areas of your project will help you decide which of the life cycle models makes the most sense as a starting point. The characteristics relate to the requirements, changes, risks, the feasibility of the resulting system, the complexity of your project, and finally, the engagement you have with stakeholders. If you know a lot of detail about each of these characteristics of a project, it might be appropriate for the linear life cycle model. By saying it's a linear model, we simply mean that many of the phases can be arranged sequentially. In other words, we have a lot of shared understanding about the project and the properties of the resulting system, and building the system can proceed in a relatively straightforward manner from phase to phase until the system is completed. So you can see how the project characteristics match up on this table. Linear models can still accommodate some change, but generally, the risks are perceived to be relatively low, and there's a lot of understanding about what needs to be done. Linear life cycle models lend themselves well to admission, discharge, transfer projects because you know you have to build specific hospital details into the software. You have to build in your units. You have to build in your beds before you can go on to build in other things in the system. So linear life cycle process works very well for those types of back office projects. Here, we show an example of a linear life cycle model. An IT project could have an initial planning phase, followed by a phase relating to understanding the requirements and documenting them, designing and implementing, testing and integrating, and finally, delivery and closing out the project. Now, please keep in mind that even though the process seems very straightforward and sequential, there are still opportunities for feedback loops, especially at each phase. And this is where your work as a project manager comes into play. We said earlier that the end of a phase could be an opportunity for you to exert management influence and, for example, review the work that went on during that phase. That process is sometimes called a quality gate or an exit gate. It requires you to demonstrate that the phase really satisfied all the objectives of, for example, the planning phase, before you move on to the requirements phase. So the linear flow of this life cycle might be a bit misleading. There's still room for feedback and control and exercising your management judgment to make sure the team is prepared to move from phase to phase. If you detect shortcomings after the phase is completed, this is a chance for you to go back and have the work completed to your satisfaction. As we mentioned in the last slide, the linear life cycle model lends itself to projects where you don't have a lot of variables or unknowns. An example used in the last slide was an admissions, discharge, transfer project where you have to build in the beds and then you have to build in the units. Those are known quantities that your stakeholders can give to you. And you can build those, show what you've built to the stakeholders, they can agree that that's correct, and then you can move on. The next reference lifecycle model in our list of 4 is called an iterative model. With an iterative model, as the name implies, the system build process includes several iterations, so it's not a single path through the project to build the system. An iterative model reflects an environment where there's still a lot known about the project and the intended resulting system, but it's not as clearly defined as in a linear model. The requirements are moderately well defined, but there still might be some lack of clarity or completeness that can be addressed with an iterative model. The iterative nature of the model allows it to accommodate more changes than the linear model. An iterative life cycle model is a good candidate when you want to understand what's possible with a single iteration and not have to build the entire system with a single path through all the phases. The iterative life cycle model works very well whenever you or your stakeholders are not quite sure what the actual product should look like when it's done. In this case, you can build part of it, show it to your stakeholders, and they can give you additional information that may change the product. You would take that information back to your team, tinker a little more, and bring it back for review until the product of that particular phase is exactly what you want. As we said, each of these reference lifecycle models represents an entire family of models, so there's a wide range of possibilities when we talk about iterative models. Again, the key idea is that there are several iterations or loops that are involved in the project and the sequence of phases that are used to build the system. Here, we want to show 3 examples of activities in an iterative model, but remember that these are just 3 points along the entire continuum of possibilities related to iterative life cycle models. We are just trying to show some of the variety of activities to drive home the picture of what iterative models look like. The first 2 examples show how different activities are included in each iteration for each loop in the process, and the third example shows how the increments or iterative systems that are being built are actually installed and used by the customer. Are they actually delivered, or are they instead remaining within your development group? One way to look at this is that you have a very large project for computerized provider order entry, and you want to provide a little bit of functionality. Let the users learn how to use the basic system, and then build upon that as you go along. An example is your first pass or your first phase could be a system for ordering diagnostic tests, so that whenever a provider or a nurse wants to order an X-ray or a blood test, they can do that in the computerized system. Then your next phase could be to provide pharmacy orders, and now they can not only order the lab test or the radiology test, but they can begin to order the medications. That's how this iterative process could go in that type of a project. The first example, again, is just one of many in this family of iterative models. As shorthand to characterize it, we're calling it a specify a little, build a little model. What's characteristic about it is that you'll have a single phase for planning and a single phase for developing high-level requirements. But after that point, you can decide that you don't want to go ahead with a single design phase because you want to understand the detailed requirements much more in an iterative fashion. Guided by the high-level requirements, you would take your first increment as providing more detail for a set of those requirements. And then, for those specific requirements you've identified in increment 1, you would design a system that will really deliver on those requirements, and then proceed to an implementation and test phase, and so on. In the same way, each increment would take off another chunk of requirements, provide them in more detail, and then design to those requirements, implement, and test. In this sense, you can think of each increment as essentially growing the system, with each increment expanding on the previous one. Notice that there's an integration phase at the end of each increment, so you always have a system that's an integrated system, and it is growing over time with each increment that gets implemented and tested. When the final increment is complete, so is your entire system, and it would be tested and ready for delivery and installation. In our previous slide, we mentioned computerized order entry systems in a modern hospital. The first step could be building your diagnostic test. Your labs and your RADs and MRIs would be built, tested, and then delivered once the customer has signed off on that increment. The next increment would be your pharmacy. All of that would be designed, tested, and signed off, and it would be integrated with your previous phase or chunk of deliverables, which was your diagnostic testing. The final phase would be moving from nurse unit clerk order entry into actual provider order entry. Again, you would do an integration of your lab and RAD and pharmacy ordering with your provider order entry. We're calling example 2 of an iterative life cycle model, build a little, test a little. It looks similar to the previous one in terms of having several increments, but notice that what's different here is that in the initial activities, there's the planning phase and a single requirements definition phase, and then you proceed to a high-level design phase, and the increments look at more detailed designs. Here, you're able to put together a high-level system architecture, but then you would pursue the detailed design only for portions of that larger design and implement and test those. This can occur in cases where there's a lot of uncertainty. For example, if you don't know which commercial products are possible candidates for delivering certain functions. You're organizing the life cycle as a series of builds or increments as before, but in this case, you're using each increment to explore different detailed design alternatives, often relating to commercial products and the risk and maturity of those products. And again, the system essentially grows as the increments are completed and integrated, and there is a single delivery of the system to the customer. Many times in the hospital or in healthcare IT, you will start out with one function of the system, knowing that ultimately you're going to implement the entire system over time. You'll integrate the first completed function with the second function, and that's how you build the system. You are building one particular function at a time and adding to it until you get all the requirements that you specified at the beginning. Example 3 in our exploration of iterative models may look very similar to the previous examples, but there's really a major difference with this one. With this example, the increments are delivered to the customer. In the prior two examples, the increments have really stayed in-house, and it was only a single delivery at the end to the customer. In example 3, you're still growing the system, but in a customer or operational environment. These incremental deliveries to the customers are often called releases because they are released to the customer. You want to explicitly identify each of them. For example, as Release 1 or Version 1, or sometimes the releases are called drops, using the same term as releases of a new album by a recording artist. Two obvious and strong advantages of this example, which we're calling develop a little, deliver a little, are first, the customer is getting a functional system earlier than if it were a complete single delivery at the end, although it's a system with less than complete functionality. The second advantage is that your team is getting the benefit of the customers' and users' feedback on these early delivered releases. This feedback is enormously beneficial to the development team. It can help the team ensure that the entire system will meet the customer's needs. It can also allow the team to fine-tune small aspects of items, such as the user interaction and user interfaces, to ensure that the users are really comfortable with the system. So by the time the entire system is delivered, it will have the most desirable look and feel for the users. This process provides a psychological benefit as well. It allows you to engage the users in helping you design a system that makes sense for them and is usable by them. Iterative models are widely used in practice. In particular, they're used with commercial products. Sometimes the separate increments are organized according to features. If you think of some of the commercial products you use, such as word processors or spreadsheet programs, and think about all the features that exist in these products, commercial developers who build these commercial products often build them in these iterative ways, where the increments are defined by sets of features that gradually grow their product into the multi-featured system that it is when it's finally released. These examples of the iterative lifecycle model illustrate the flexibility that you have in the lifecycle by using the separate increments and iterations to develop a system that will be satisfactory when it's ultimately delivered to the customers and users. Whether you build healthcare IT products in-house or you buy off the shelf, be sure to ask your vendors or your programming staff how often their upgraded versions come out. If they say they don't have a real version control process, that's a red flag. Or if they say they release upgrades on an as-needed basis, that is another red flag. Most companies will have a defined process that they go through and will have releases either once or twice a year. That schedule gives you time to implement the releases so that your stakeholders will not become confused and upset by the number of releases that they get every year. Our third family of reference lifecycle models is called adaptive. Adaptive lifecycle models, as the name suggests, are designed to be very flexible and very responsive to changes. As the saying goes, the only constant is change. Even when projects appear well understood and stable at the start, they have a way of changing once the project gets underway. It can be vendors going out of business, an organization merging with another organization. There may be a new law or regulation that you have to comply with. Key personnel staff or a lead designer may leave, or maybe a new product or technology comes on the market. All these changes are going on while you're building your project. Adaptive lifecycle models provide you with the flexibility for dealing with these changes. One important subclass of these models is the one that helps you deal with the uncertainties of these requirements. At the start of your project, your customer and your user community may not be entirely sure which features of the health IT system will be needed. An adaptive model may be the appropriate model in these cases. A characteristic of these models is that there is usually a lot of stakeholder engagement. Your customers and user communities will be proposing changes and telling you what's needed in the system. You may need to emphasize the importance of having stakeholder and customer involvement as essential elements of this adaptive lifecycle model. As the table points out, another key characteristic is that the plans may change. This is in contrast to the prior two models where the planning was fairly straightforward with some opportunities for iteration. But now it's a case where even the planning is challenged to be really complete. Adaptive models are very useful for the times that you go live with a system. You can have your linear process to build and test the system, but you might want to build in an adaptive model for the immediate time after you go live. As issues are identified in the system, you can use that adaptive model to make changes and show them to your stakeholders so they can approve it, and this way those issues are turned around very quickly. This concludes Lecture B of Project Life Cycles. In summary, we have reviewed the 4 different project life cycles and how their characteristics differentiate them. We have used specific project examples to illustrate how some models are more appropriate for different types of projects and how you would apply them.